Hi, welcome back now to derivability. Let's take a look at some more mechanical engineering here, or definitely a lot of physics here, and figure out the kinetic energy of a rigid body in planar motion. Okay. Now, if you've had introductory physics, you might suspect correctly that there's going to be a contribution here due to the translational motion of the body, and we're going to keep track of that via its center of mass, which I've labeled G. But there's also going to be a rotational component to this kinetic energy. Okay, when I say component, I don't mean a vector component as such. Kinetic energy is a scalar. All right, but there's going to be a term in the equation. Okay. Now, one thing we're going to use here is this equation for V sub IO. Okay, if that is not familiar to you, okay, I have a video did a couple of weeks ago on the kinematics of planar rigid body motion. Okay, I'll just try to explain this real quickly here, but because the body is rigid, point I can only have rotational motion relative to any other point in the body. Okay, and that's where the omega cross R term comes from. Okay, but I explained that in a bit more detail in the previous video. Okay, all right, so you probably, if you've seen those other videos, you probably recognize the scheme here, the diagram. Okay, and the kinetic energy of this mass element, I. A lot of engineering books use T for kinetic energy, capital T. So T sub I is 1/2 m sub I times V sub IO squared. Okay, and the way we're going to do this V squared is by taking the dot product of the vector V sub IO with itself. Okay, that is, we're going to take a dot product of those two terms with themselves, each other. Okay, and after we do that, we'll fill that back in up to the kinetic energy equation. Okay, all right, so I've got that prepared down here. So imagine taking V cross R sub IG plus V sub GO dotted with itself. Now, there's really not that much different about doing this than there is multiplying a binomial times itself, a binomial square. Okay, so let's just start with what we would have for a binomial square. Okay, we're going to have that first term dotted to itself. Okay, then we're going to have 2 times the product of the two terms. I'm going to write the V sub GO term first here, maybe a little differently than you are expecting me to do that. Okay, and then the square of the last term, or the dot product of velocity GO with itself. Okay. Now, the first term and the last term actually are going to simplify quite a bit, or the first term will anyway. And then after that, when we plug back into the kinetic energy formula, then we're going to take a sum over all mass elements, m sub I, or really it's more like an integration. Okay, so let me create some clean space, and then we will continue. Okay, so we've got some clean space here, and the place where we stopped off, back up at the top. Okay, now let's simplify where we can here. All right, now first, omega cross R. Okay, generally this is just going to be expressible as an R times omega in terms of its magnitude. Okay, that's because if we actually did a cross product, omega k, in the third dimension pointing toward you, let's say, cross R sub IG, well, this would be a tangential velocity perpendicular to R sub IG. Okay, right there. Okay, velocity IG. All right, and because we're taking a dot product, everything's a scalar in the end, then we don't need to worry about directions. Okay, so this first term here, when I take this dot product, is really just, I'll write it with the omega term first, omega squared r sub ig squared. Okay, the last term, well, it's a dot product of a vector with itself, so it's the squared magnitude, which is a scalar. I'll just write that as v sub go squared. All right. Now I think we are ready to plug this back in to our formula for t sub I. Okay, 1/2 m sub I, and then times the whole thing here. Well, omega squared r sub ig squared. Okay, now that middle term, really not much I can do with that at this point, although once we consider the integration, some good things will happen there. Okay. Oops, I don't have to write the vector sign there. That's a scalar. All right. So now to get the total kinetic energy, okay, you can think of it as two ways, which in this case are roughly equivalent. We can take the sum over all such elements I, and if we imagine them to be infinitesimal, it's like taking an integration. So I'm going to do a couple of things here with these three terms. For each term, if there are any constants with respect to the integration, I'm going to bring them outside the integral. And also, maybe before I do that, I'm going to distribute the 1/2 m sub I through the parentheses. Okay, so for this first term, again, distributing the 1/2 m sub I through there. Okay, I've got omega squared times a 1/2, okay, constants with respect to the integration. Then I'm going to be integrating over the rigid body of r sub ig squared dm. And if it helps, think of it as dm sub I. Okay, second term, I'm going to have a 1/2 canceling with a 2. Okay, now the v sub go, that's the velocity vector of the centroid. Okay, it has nothing to do with various other points, it just is what it is. Okay, then dot. Now the omega here is also, as before, is a constant with respect to the integration. Okay, and then I'm taking the cross product of that with this vector r sub ig and then dm sub I. Okay, of course those have to be inside of the integration. Okay, and then finally the last term here, I have plus 1/2 v sub go, again constant with respect to the integration, and then integral of dm, or dm sub I. Okay, all right. Well, let's resolve what each of these integrations is equal to. Okay, I'll do the easiest one first. Okay, the integral of dm is just the total mass. Okay, and then when we tally this up here in a few minutes, you'll kind of recognize that term. Okay, now this integral, r squared dm, is a rotational inertia. And since the r's are being measured with respect to the center of mass, this is the rotational inertia about the center of mass. Okay, now the integral in the middle, this is maybe a little tricky here. Okay, what you have to remember, I'll kind of write this parenthetically up at the top. You may recall that to figure a centroid, say x bar, in some notation, you have 1/m times the integral of x dm. Now, other than this being a vector, r, and the fact that I don't have a 1/m here, okay, if I multiply both sides by m, I can get right m times x bar equals the integral of x dm. Okay, well, basically what I have here is I have an integral of some coordinate dm. There's also a y dm in there in terms of vectors and unit vectors. Well, this is going to be the total mass times the position vector of the centroid. That's what this bar often means. Here in this double subscript notation, position vector of the centroid, but we are measuring with respect to the centroid. Okay, so we're basically finding the position of the centroid relative to the centroid. Well, wherever you go, there you are. And that is where the centroid is with respect to itself, 0. So this middle integration just drops out when you're measuring with respect to the center of mass. Okay. All right, we're almost there. and it's going to mop up real nicely here. So let me create some more clean space, and we'll be just about finished. Okay, well, I left our previous step down at the bottom where it was, and created just enough clean space, I think, for us to finish this up. So let me start with the third term here. We'll do this one first. It's going to make more sense to do that first up top. Okay, well, what I have here is 1/2 m, that's the total mass, times velocity GO, that's the velocity of the centroid relative to some fixed origin here, squared. And in fact, I guess I don't need that vector sign. I could have the vector sign if I wanted, but I don't really need it because I'm talking about a scalar. Okay, and plus another term. Well, this we might call the translational kinetic energy of the object, okay, of its center of mass. Okay, and then we've got another term, the one from the beginning, right here. So we've got a 1/2 and then I sub g times omega squared. And as you're probably going to guess, we could think of this as the rotational kinetic energy. Okay, now strictly speaking, because it's an I sub g, okay, this is being measured about the centroid, or about the center of mass. Okay, and then we get the total kinetic energy. All right, now there are a couple of alternative ways of writing this. Okay, the way I've written it here, this is the most general way. Okay, now there's another way which is completely general. Okay, you have to do a little working to get to it, but you can write this as 1/2 I omega squared if the I is about what we call the instantaneous center. Okay, so in other words, if we can figure out that at the instantaneous center, the point about which this is momentarily rotating about, then we can use the parallel axis theorem to figure out that new moment of inertia, and we can just use a single term here. Okay, so a reminder here, you have to use the parallel axis theorem to find the instantaneous center. Okay. Also, this works if you happen to have a fixed point. In other words, there is a point about which this is actually attached. There's a fixed axis passing through some point P. Okay, and then the same formula works if you happen to have a fixed point. But since we're concerned with the general motion in the plane of a rigid body, you almost never have a fixed point. You will have an instantaneous center that might change from moment to moment. Okay, it's true instantaneously, but you may not have the fixed point. But the same formula should work whether you have a fixed point, which is more than an instantaneous center. It is kind of a fixed center. Or an instantaneous center. Or, of course, you could always go back to this truly most general formula. Okay. All right. Well, that's going to do it here. Hope this has been helpful and maybe even some enjoyable for us. Okay. Thanks for sticking around to the end here. Please share this with some classmates and friends who you think might benefit from this, who are studying some engineering or physics. Give me a subscribe. Love to have you on board. And we'll see you again next time on Derivability.